Welcome back to geometry. Hope you had a little break from math class and hope you're ready to get back at it. Okay, we're going to get ourselves started on section 10.1. Before you left, I had given you a new assignment sheet for chapter 10, but I'll attach that to your Google Classroom site so that you can pick up a new one if you've misplaced that. All right, but we'll get ourselves going here in chapter 10. And chapter 10 deals with a new geometric figure that we've touched on a couple of different times, but we're just going to focus on it now for this chapter, and that is a circle. Okay, so that's going to be the topic that we're going to be talking about throughout the chapter. Alrighty, so we'll start with the definition. Circle is the collection of all points equidistant from one fixed point. Okay, so if we were in class, what I would do is I would dig out a compass, just like you guys would have done many of your construction projects with this year. And I'd construct a circle by putting the fixed point on the chalkboard and then using the arm of the compass to show all of the points that are equidistant from that one fixed point. Using my iPad, I can show you a circle. And the idea would be that from one fixed point, I'll ask you what that's called in just a minute, the distance from that point to any one on the circle, so the straight line distance from that fixed point to here, or that fixed point to here, or that fixed point over here somewhere, that distance is always the same. No matter what direction we go, that distance is always going to be the same. Okay? So what is that fixed point called? That fixed point is called the center of the circle. So I'll just use a C to represent the center. And then the collection of points that are equidistant, that equidistance is called the radius. All right? And we usually use a lowercase r to denote our radius. So every single point on the circle, this one right here, and this one right here, and this one right here, and this one, and this one, and this one, and this one, and all of the others, all of these points are then equidistant from the one fixed point. And that's our definition for a circle. Okay? Now, there's going to be some other lines that we need to concern ourselves with when dealing with a circle. So let me scroll this up. Let me get you guys a new circle drawn here. Get a decent sized one. All right. And I'll start listing out some of the different terms that we're going to need to know. Obviously, we already have circle. I'll just repeat these two. I need you to be able to identify the center of a circle. I need you to be able to identify the radius of a circle. And then there's a few others. Diameter, chord, tangent, and secant. Those are all terms I'm going to need you guys to understand when we're dealing with a circle. Okay? All right, so let's go through them. The center, again, is the fixed point. I'll use a C there. From which all of the distances to the circle are equal. Radius, again, is the distance from the fixed point, center, to any point on the circle. Again, we'll use a lowercase r traditionally for that. Diameter is a line that goes from circle to circle. All right, so it goes between 2 points on the circle and passes through the center. So we usually use a lowercase d to represent a diameter. So radius from the center to the circle, diameter from circle to circle that goes through the center. That goes through the center. Okay, the fourth one is called a chord. And a chord is a line that goes from circle to circle from one point on the circle to a second point on the circle, but does not pass through the center. Okay? So radius from the center out to the circle, diameter from circle to circle passing through the center, and a chord goes from circle to circle but not through the center. So we're just left with two others, and I'm going to scroll up the screen just a little bit to draw a new picture. Okay, so there's our circle, and now I'm going to demonstrate a tangent and a secant. Now tangents and secants are going to be lines drawn from a point outside of a circle. So I've indicated a point P that's outside of the circle, and if we draw a line from that point that just, sorry, I hit the wrong button on my iPad. Let me try that again, guys. There we go. If we draw a line from point P that just hits the outermost point of a circle as it goes glancing by, that's called a tangent line. A line from a point outside of a circle that hits the circle at just one single point is called a tangent. And then a secant line is a line drawn from a point outside of a circle that hits the circle twice. So a line drawn from outside of a circle that hits a circle twice is called a secant. All right? And those are the definitions I'm going to need you guys to be able to work with and have in your mind. Obviously, you guys have them in your notebook as we move forward through the rest of the chapter. Okay? All right. Now, a couple other minor definitions that we'll need to work with. And it just popped in my head. If I'm ever moving the screen too fast, please just be aware that you can pause the video at any point to write down anything you need to in your notebook. Feel free to just hit the pause, write down a definition or an example, and then just click the play to resume. Okay? But a couple other minor definitions that we'll also need, other than center, radius, diameter, chord, tangent, and secant. A couple other definitions. The first one is called concentric circles. Concentric circles. And the second is common tangents. Okay. Now, both of these definitions, not real important, but useful from time to time. First, the concentric circles. Let's in fact write down the definition first. These are just simply going to be circles with a common center. Circles with a common center. So let me see if I can draw a couple of concentric circles for you guys. So here's one circle. Now I'm going to draw another circle off to the side. But if I pick this one up and slide it over top of the first one and position them carefully so that the two centers are right on top of each other, then those circles are considered to be concentric. One circle on top of another one with a common center, the same center. Okay, and I can do it not just with two, but I could also do it with, or try to do it with three. My first center disappears there, but I'll try and position this one okay. And so here we might have a point C. That's the center for the first circle. So this would be the radius of one of the circles. The center for a second circle, that might be the radius for a second circle. And then also the center for a third circle where the radius might be something like that. Okay, so those are concentric circles, circles that have the same center, common center. Okay, and then the other definition is common tangents, and I need to demonstrate that by pictures. So I'm going to draw two circles. I'll make these a bit smaller. Okay, and what we're going to ask you guys to do on just a couple of problems, not a big deal, is draw lines that would be tangent to both circles at the same time. So tangents which are, in fact, let's change that up, guys. Let's change that up. Let's deluxe eraser that. Let's get rid of the word tangents. Let's replace that with the word lines. So lines which are tangent to multiple circles. Okay? All right, so that's probably a better definition. And so with my example here of two circles drawn kind of left and right of each other, are there going to be any common tangents? Can you guys draw one line that would be tangent to both circles at the same time? Well, try something like this. Would that be a line that could possibly hit the larger circle at one point and the smaller circle at one point? Sure. And then is there another? I'll try to draw it. Try to draw it here, see how this looks. All right, could you see that that might be another line that would hit us the bigger circle once and the smaller circle once? So in this situation, we could have circles with two common tangents. And so, the thought might be, well, what's the largest number of common tangents you could possibly draw? Are there any others? And someone may have already found them. I could switch colors just so they could be highlighted a little bit. Are there any other common tangents? Well, we could also draw one like this, right? That could hit a circle 1 point here and 1 point here, and then another one. Drawing something like that that might hit circle 1, circle. Okay, so maybe altogether we'd have 4 common tangents. All right, doing okay so far? All right, so quite a few definitions, well, like we're used to. And then what we do is we finish with 2 theorems and some numerical problems that go along with each of those. Okay, so finish off the section with 2 theorems. First, number 10.1. And the theorem for 10.1 goes like this. In a plane, the tangent to a circle is perpendicular to the radius at a point. Okay, now might not sound very clear, but when I draw you guys a picture, you'll see how this is going to work. So if I get you a circle and we draw a tangent, so we pick a point outside of the circle somewhere, and we draw the tangent line, so a line that just glances off the outermost point of the circle as it goes by. Okay, that would then be called a tangent. What this theorem says is that tangent line is always going to be perpendicular to the radius at a point. So now if I were to draw the radius in to the same place, to the same point, so if I draw this radius in here, what the theorem says is the tangent line and the radius are going to be perpendicular to each other at that point, at the common point. Okay? So that's our theorem 10.1. And then we'll have some relatively easy numerical problems that go along with that theorem. And again, feel free to pause the video if you need to jot down that theorem or the diagram. But previously I've written out a couple of, a couple of numerical problems that where we can use theorem 10.1. So as an example here, we have a circle. What I've done is I've drawn a tangent. So this line that's 96 units long is a tangent. And then we've drawn the radius to the same point. So the point here, the point that we're talking about is this one right here. So the radius and the tangent are drawn to the same point, and the theorem says that they're going to be perpendicular to each other. Okay? Well, if they're perpendicular to each other, then we know that if I also draw the line from the outside point to the center, I create a right triangle. And if I have a right triangle, that leads us to problems involving Pythagorean theorem. All right? So using Pythagorean theorem, we can create some numerical problems that force us to use theorem 10.1. Okay, I'm just going to ask out loud here. Does everyone know what side the hypotenuse of that triangle is? Okay, always across from the 90-degree angle, so hopefully that you'll remember. And therefore, Pythagorean theorem is going to be leg squared plus leg squared equals hypotenuse squared. And with our calculator, we can start to do the algebra here to solve. 96 squared is 9,216. 100 squared is 10,000. So we'd have to move positive 9,216 to the other side by subtraction. We get 784. And then to get rid of the power of 2, take the square root of both sides. So r is going to be equal to 28. So the radius of our circle in this example is 28. Okay. Again, if I'm moving the screen too fast, feel free to pause. But just going to bop through a couple more examples using that theorem. Again, the same situation, we have a tangent line. So here, this is the tangent line. This, of course, is the radius. So if they're drawn to the same point, the theorem says they're going to be perpendicular to each other. So therefore, again, if we draw in the line from the point to the center, we have a right triangle. Okay, just made this one a little bit tougher because when I ask you for the hypotenuse, I just need you to notice that the hypotenuse is broken into two chunks. This chunk, r, and then this chunk, 16. So when we write down Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. Normally the hypotenuse is either a number or a variable, but in this case it's two put together. So what we'll have to do is add r plus 16. Okay? Now on the left-hand side of the equation, not bad, we just need our calculator. 32 squared is 1,024, no sweat there. But what is a problem is the right-hand side. How do we square a binomial? How do we raise this binomial to a second power? And probably the easiest thing for everybody to do is just write it down twice. A power means multiply by itself. So write it down twice and then FOIL. So if we FOIL, what we'd have is the firsts, the outsides, the insides, and the lasts. Okay? Looks like it's going to be a terrible equation to solve, but notice if I try moving, let me pick my laser pointer. If I try moving this r squared right here to the other side, I'd have to subtract. And what's nice about that is the r squared cancels on the left-hand side and the right-hand side. So all of a sudden, instead of a second-degree equation, what we'd have instead is a first-degree equation. 16 plus 16 is 32r. So all I need to do then is move positive 256 to the other side by subtraction. We get 768. And then to get rid of times 32, divide by 32. And so r then is going to be equal to, let's see, 24. So the radius of this circle then would be 24. Okay? Looking all right with everybody? And I've got one more example problem, very similar to the previous one, just the numbers are a little bit larger. So if you want to just follow along, if not, you can skip ahead a couple of minutes. Excuse me. But this one again, I made this one a little bit tougher because the hypotenuse is again divided into two chunks. This piece that's 49 long, so from the outside of the circle to this point is 49, and then the inner part, which of course is the radius again. Okay, so with a little bit tougher numbers, Pythagorean theorem then would be leg squared plus leg squared equals hypotenuse. Again, you got to add those two chunkers together, squared. Okay? Now, it looks like a hassle, but with your guys' calculators, not so bad. 63 squared is 3,969. And then again, to square a binomial, write it down twice, just as in the previous example. And FOIL. So 49 times 49, 2,401. The outside's 49 times R. The inside's 49 times R. And the last's R times R. Okay? Again, it looks like it's going to be a tough one, but just as in the previous example, when I try moving the R squareds from one side to the other, they cancel on both sides. So what we'll have then is 49 plus 49, 98R. And if I move the 2,401 to the other side by subtraction, I would be left with 1,568. Yep. So to solve this, divide both sides by 98. And we get a value for the radius of 16. Okay, so there's a couple of numerical examples using the first theorem. All right, so I'm just going to slide back and now give you guys the second theorem for this section. All right, so theorem 10.2. Theorem 10.2. And this one says two tangents drawn to a circle from one point are equal. Two tangents drawn to a circle from one point are equal. So again, let me get you a picture of this for your notebook. We have a circle. We pick a point outside of the circle somewhere, so I'll pick this point right here, and we draw the tangent above and below. Okay, and what this theorem says then is that the two tangents drawn to the circle from this one point, I'll call it P for point on the outside, are going to be equal. So the length of this segment and the length of this segment are going to be equal to each other. Okay, and that's always going to be true. Alrighty? And so, excuse me, to finish off, let's just take care of a few numerical problems then dealing with this theorem, and we'll call it a day. All right? So as an example here, what we've got going on is two tangents drawn from one point. So again, if I call this point P, we have a tangent drawn above, right? That's 4x plus 7 long. And we have this tangent drawn down below, that's 7x minus 8 long. Now what the theorem says is this tangent segment and this tangent segment are equal. Therefore, if I use our tick marks like we so often do, those two segments will be equal. And that what that allows you to do algebraically is say that one tangent, this one, therefore has to be equal to the other tangent, that one. Giving you guys a real easy equation to solve. We can move the x's to one side. I'll go right. The numbers to the other side. And then divide both sides by 3. So the value for x that makes this true then is 5. Okay, so relatively simple theorem, I hope. Just the two tangents drawn to the same circle are equal. Okay, now on the second example, all of a sudden it looks like I've done something very complicated, but it actually isn't. It actually isn't very complicated. Even though I have two circles and three tangent lines, so I've got one tangent line here, if you see the red arrow, tangent line in the middle, again, See the red arrow, and then a tangent line over here. So I have 3, 1, 2, 3 tangent lines. So what's the deal? What's going on here? Well, if you just look at the bigger circle to your left, there's 2 tangent lines drawn to that circle from one point. Again, if you want me to, I could call this point P on the outside. So 2 tangent lines drawn to the same circle. So if we call this circle number 1, those 2 tangent lines have to be equal. The theorem says 2 tangents drawn from one point to the circle have to be equal to each other. So these 2 segments, the 6x plus 5 and the one that doesn't have any numbers or variables attached, they have to be equal to each other. But then we have a second circle. We have circle number 2 over here. But again, to that circle, there's 2 tangents drawn. So therefore, we would have to know that the tangents have to be the same length. Right? So if these 2 tangents are the same length and these 2 tangents are the same length, that would then tell us that 6x plus 5, the tangent furthest to the left, would have to be equal to 37 minus 2x, the tangent furthest to the right. And if you, I'm not sure if you'll remember, but that's essentially a transitive property situation going on. And then again, the equation that's formed is very easy for you guys. Variables to one side. This time I'll go left. Numbers right. And divide both sides by 8 to get the variable by itself. So the value for x that forces this to be true then is 4. Okay? And finally finish off the day with one last example. Just going to make the solving part of this one just a titch tougher on everybody. But the idea is the same. From this point, outside of a circle, we drew the 2 tangents. The theorem says that those 2 tangents are the same length. So this tangent and this tangent have to be the same. So algebraically, what that allows us to say then is the length of one tangent, x squared minus 1x, has to be equal to the length of the other tangent, 6. And again, that gives you guys an equation that you can solve. Now, for everybody in 5th hour, this is going to be a little bit tougher to solve. Everyone in 6th hour, you should be okay. To solve this second degree equation, we'd need to move the positive 6 to the left-hand side by subtraction, and then factor the trinomial into 2 binomials. Right? And in this case, we'd be looking for what numbers multiply to get negative 6, and at the same time would add up to negative 1. And the numbers that work are negative 3 and positive 2. So that when you set each of these then equal to 0, creating 2 little equations, and solve, we'll get x equals positive 3 and x equals negative 2. Right? And you can see by putting 3 in for x or negative 2 in for x, both of these yield equal tangent segments. Okay? So hope you're doing okay. Let me know if you're having troubles. If you have questions, you can call or email me every afternoon, and we'll just move on. Give me any suggestions you might have as we move forward. Okay, so hope you're having a good day. Hope this finds you guys well. Hope to see you soon. Bye.